Hi there, my name is Eric and I'm Professor of Chemistry at the University of Marburg in Germany, and I want to tell you a little bit more about our research program. Specifically, I want to tell you about the way we design chiral transition metal complexes used in asymmetric catalysis. Now, what you learned in Chemistry 101 is that the standard way to create chiral metal complexes then used in asymmetric catalysis is by carefully designing a tailored ligand and combining it with a central metal. And we thought, why using a complicated chiral ligand if a chiral ligands can already do the job? Because in many cases, upon assembling a chiral ligands around a central metal, you generate a stereogenic metal center which then is responsible for the overall chirality of your transition metal catalyst or complex, and this you can then use for asymmetric catalysis. That's exactly our approach. And this approach is not better than the conventional approach, but it provides new opportunities to consider certain scaffolds and topologies for using in asymmetric catalysis, and that gives us the opportunity to discover novel reactivity and hopefully also novel reactions. And I think that's what we could really demonstrate over the last few years. Now, in my last video, I was talking a little bit about the complexes shown here on the bottom left, bis-cyclometallated rhodium and iridium complexes, and I told you that they are really suitable for combining Lewis acid catalysis with photocatalysis. Today I want to focus on the complexes shown here. Now we have a central ruthenium, and the ruthenium is not cyclometallated but coordinated to two bidentate pyridyl NHC ligands in addition to two labeled acetonitriles. And although the complex on a first glance look very similar to these bis-cyclometallated rhodium and iridium complexes, they have completely different personality, very different reactivity, no photochemistry, but they are very suitable to catalyze nitrogen chemistry, and I want to tell you a little bit about this. Now, let's take a closer look at these ruthenium complexes. So we have two bidentate ligands that are configurationally inert. They coordinate in a, I would say, helical fashion with a formal stereogenic metal center, and in addition, we have two monodentate acetonitrile ligands. Overall, we have an octahedral coordination sphere, and due to the stereogenic metal center, we create overall chirality, and the complex can exist as image and mirror image. And this in the middle is our mirrage plane. Now, why are these complexes so inert? That is really a good question, and I just want to basically show you the three-dimensional structure. It gives you a little bit an idea about the overall geometry and topology, and also some reasons of the high stability. So you can see here, you see the two bidentate ligands, the two monodentate ligands, and a very an interesting aspect is this substituents on the NHC, this mesyl group. You can see the mesyl group of the one ligand stacks against the pyridyl group of the other ligand. So we have not only the coordination to the central metal, we have also interligand pi stacking. So we get a very compact coordination sphere. And I stress this because this is very important. We don't have chiral ligands, so we require that these bidentate ligands stay in place and don't isomerize, because otherwise we would lose the chiral information and we could not obtain any enantiomeric excess. or we would reduce our enantiomeric excess if we see any decomposition in the course of catalysis. This complex here and its derivatives, we use them in a reaction at temperatures above 100 degrees. So above boiling water temperature, these complexes do not decompose. That is really fascinating. Now, I mentioned that they can do nitrene chemistry, and I want to tell you a little bit about this. So, what are nitrines? Nitrines are monovalent species. They can exist as singlet and triplet nitrene. So we have one substituent R, and we typically consider the nitrogen being sp2 hybridized. We have two sp2 orbitals and one p orbital. In addition, of course, to the sp2 orbital, which forms a sigma bond to the group R. Two paired electrons, lone pairs in sp2 orbitals, and then in a vacant p orbital. This is the singlet nitrene. And you can also have alternatively a triplet nitrene in which the in which we have two unpaired electrons. And again, if we look at the orbitals, one lone pair sits in an sp2 orbital, and then we have a single electron in the in another sp2 orbital and a single electron in a p orbital, and that's a so-called triplet nitrene. And these nitrines are highly reactive species. Why? Because, as you learned in Organic Chemistry 101, they don't have an electron octet. They're electron deficient. So they're yearning after basically interacting with electron-rich species. So they're highly reactive electrophiles. And for example, they even want to react with sigma bonds, such as CH sigma bonds. So if you have a nitrene and you react it with a CH bond, the nitrene can just insert into, this is a carbon, into the CH bond. This is a CH insertion. And that's a really interesting reaction because you convert a CH bond into CN bond. And that's a really valuable transformation. You might know that amines are very, very important functional groups, and many bioactive compounds have somewhere an amine and even connected to a chiral center often. So, what's the problem? The problem is they're so reactive, these nitrines, that they will react with a lot of functional groups. CH bonds in a very unselective fashion. They can add to double bonds forming aziridines. They can react with lone pairs, for example on sulfur, on phosphine. They can induce rearrangement and so on. So as free species, they are not that useful, but you can tame them. And how do you tame them? Taming the nitrines, you can tame them by reacting with a metal, and you form a nitrene complex, either as a singlet, and we call it singlet nitrenoid, or as a triplet nitrenoid, and one electronic description would be like this triplet nitrenoid. So in the singlet nitrenoid, think about you have a singlet nitrogen that coordinates to the metal with one of the sp2 lone pairs, a sigma donor bond, and then a pi back bonding from a d orbital to the vacant p orbital at the nitrogen. That gives us formally a double bond between the metal and the nitrogen. If you interact formally a triplet nitrene to a metal, you have a sigma donor with the sp2 filled sp2 orbital, and then you have a partially pi back bond to the mono occupances to the p orbital at the nitrogen that has already one electron in there, and that gives you, of course, a free electron in the in one sp2 orbital. It's a nitrogen, so that's why I draw here the radical. Good. And our chiral-at-ruthenium complexes or catalysts, they're very, very suitable to interact with nitrines and to control the reactivity of these nitrines, including the stereo control. And I want to show you just one recent work that we published, in which we use as substrate these, I go to the pen, these N-benzoyl-oxyurea, and they basically, when you basically react them with, for example, this ruthenium complex, we obtain a CH amination. This CH, you can see, is converted into the CN bond, even in an enhancer selective fashion. And the really fascinating aspect is, if you change one substituent on this pyridyl moiety, you make it bigger from CF3, you go to a triacyl group. We don't obtain CH amination, but instead we observe CH oxygenation. So depending on one substituent in the catalyst scaffold, we can convert a CH bond into a CN or CO, and even in an enhancer selective fashion. So how is that possible? Very simple. CH amination pathway. We start with the ruthenium. The ruthenium activates this functional group here. So in presence of the base, we basically get rid of benzoic acid, and that gives us this triplet nitrenoid that I was mentioning in the previous slide, with a radical character at the nitrogen, and that can now abstract a hydrogen from the CH bond. We break it homolytically, and we generate this carbon-centered radical, and this carbon-centered radical can now recombine with the nitrogen, and there is still additional spin on the ruthenium and the nitrogen, so that it's kind of a radical recombination, and we generate the CN bond, and then the ruthenium just basically dissociates, and we release our product, shown here as product 4. That's a CH amination pathway. How about CH oxygenation? Same mechanism. Ruthenium catalyst activates this benzoyl oxyurea functionality. We get our nitrenoid intermediate with spin radical character of the nitrogen, homolytic cleavage of the CH bond, and we get exactly the same intermediate that I was mentioning in the previous slide. However, the difference here now is that the ruthenium for the CH oxygenation is bigger, more bulky. We have triacyl groups on the pyridyl moiety. So, and we think, and this is our basically hypothesis, that because of this very, very bulky ruthenium fragment, the radical recombination that happens in the CH amination is slow, and instead what happens is that we have a rotation around the CO bond, and this rotation brings the oxygen then close to the carbon radical here, centered radical, and the oxygen now recombines with the radical, not the nitrogen, and we get a CO bond. And then ruthenium dissociates, and we get this aminocarbonate which hydrolyzes, and we obtain as a product this cyclic carbonate, generating a CO bond where formerly there was a CH bond in the starting material. So really fascinating. Depending on small changes in the catalyst, we can achieve CH Amination or CH oxygenation? I think that's a fascinating mode of action for our catalyst, and the chirality of this chiral fragment, so the stereogenic ruthenium, leads to asymmetric induction, so that the CO bond is formed in a non-racemic fashion. So I hope you found this interesting, and thank you very much for listening. Bye bye.